You've seen that slope fields give us qualitative information about a differential equation. But is there a way to leverage this qualitative data to get a quantitative solution? The answer is yes. This mathlet illustrates a numerical method called Euler's method, which approximates solution functions based on slope fields. How does it work? The idea is to use linear approximations on small intervals and to take a new approximation at the end of each interval. To illustrate how this works, first we choose an initial value by clicking anywhere on the screen. Second, choose a step size. Here I'm using the smallest step size because linear approximations are most accurate near the point of approximation. Euler's method takes a linear approximation at the initial value using the slope field to determine the value of the derivative at that point. I'm going to zoom in so this is easier for us to see. So you see a straight line here. That's the linear approximation at the initial value. And this width, this change in x here, this is our step size. Then the next step is to repeat the process, but the new starting point is the end of the linear approximation. So we step again and continue. And what you see is that we get a piecewise linear function that follows the slope fields. I'll zoom back out and continue so you can see the trend of the solution function. Next, I'll click to see the actual solution to this differential equation with the given initial value. The solution curve appears in blue, and you can see that the two solutions are quite close. If I zoom in, you can see that they start off really close and then some error begins to accumulate. But overall, this approximate solution is pretty good. It could be better if we used a smaller step size. You can see that if we use a larger step size, the approximation is pretty bad. You may be wondering, how does the mathlet generate this so-called actual solution curve, and why aren't we teaching you that? Spoiler alert, there is no formula in terms of any functions that you know for this solution curve. What we're calling the actual solution here is another numerical approximation that is very similar to Euler's method, but which uses a fourth-order polynomial approximation rather than a linear one. In the next problems, you're going to work out the formulas for Euler's method, and we'll generalize the algorithm after you've had a chance to work through the algebra yourself. After that, you'll have an opportunity to play with this mathlet.